All right, so it looks like we got the next packet going. So this is the second packet, packet number 2. And if I can kind of keep this pace, I should cover one packet each week, and we should get the first 4 packets. Don't forget also that, again, with the whole grade thingy, it's kind of a slow process. I don't know why it's taking so long. It's not me. I'm just waiting for well, actually, you know what? I spoke to the other teachers this week, and I think all 3 of us had a different idea on how this was supposed to be done. So it sort of just came out that we actually don't know how we're supposed to do the grades. So I know I've been telling you that most of the week, last week. So again, I'm gonna have to change that as it goes along, because yeah. But anyway, you know, as long as you do the work, as long as you stay caught up, then you won't have to worry about anything, really. So let's go ahead and get started. I'm not sure how long this is going to be, but we're probably going to get through this first page, and then we'll move to the next thing. All right, and as always, if you have your packet, go ahead and open it up and start working on copying this down. I think this should be like the first page, and we're just going over different types of reasoning, and in this case, conjecture. For packets, again, you know, the best way to get them is to just show up to the building and pick them up, have them picked up. Okay, I mean, I don't know if we're mailing them out. I think we mailed a few of them out, but I think if you're a late joiner, then you will have to wait, or you will have to show up to the building to get it. I know they want the new ones by tomorrow, so I think the next week's will be going out. And what else? Yeah, and don't forget too that you're supposed to have up the last week you were supposed to get 3 packets. You're supposed to get the pre-test, the week 1 and the week 2. Hopefully, if I can get things going right, I could probably get the week 3 and 4 packets out as well. But again, just turning in any work is good. And let me just I think I still have some people still trying to get in or don't know where to go. Okay, anyway, back to here. So hopefully you got most of this down, because I'm going to start going over it, and I'm going to start going down the worksheet as we move along. All right, so inductive reasoning. So inductive reasoning is kind of like taking what you can see and making, basically having an idea about it. So making a conclusion based on observation and pattern. So taking, again, what you see and making a conclusion about it. Right, so you can't, well, you shouldn't be making up things that, without any evidence, really. So it's just basically using evidence to make your conclusion. Conjecture, so a concluding statement reached using inductive reasoning. So, okay, a conjecture goes with inductive reasoning. So that's basically, how do you prove it? Looking at it, what did you do to get it? What was how did you get that outcome? So here, let's go ahead and do some of these here. So find the next 5 terms of the sequence and then write a conjecture. So, well, here you can see the whole thing. So we're not gonna, again, this is largely a review for you guys. So you've probably seen this before, and you would have had a regular class, a whole regular class kind of dedicated to this stuff. But if you've already covered it, then you probably have already seen this before. So this is just review, hopefully, for you. So if we start from 38 to 31, 24, 17. So we got to look at that pattern and think to ourselves, what's going on with that? Okay, well, you can see right here, it goes down by 7 each time. So we're subtracting 7 from the previous term. And yeah, from 38 to 31, yeah, you're subtracting 7. From 31 to 24, also subtracting 7. 24 to 17, subtracting 7. So if we continue that pattern, we get 10, 3, -4, -11, and -18. So that's all that's happening is we're just subtracting 7 from each time, from each term. All right. Whew, kind of sleepy today. What a heck of a weekend. Sorry about that. All right, next one for this one here. So 2, 5. Okay, so what did we do from 2 to 5? Can't really tell just looking at those two. So if we go to 5 to 11, what could have happened from 5 to 11? Well, you'd have to add, okay, so from 2 to 5, you'd have to add 3. From 5 to 11, you would have to add 6. From 11 to 23, you would have to add, let's see, 11, 13. So there's some kind of weird thing going on here. So what they said is to generate the term, the next term, double the previous term and add 1. Double the previous term and add 1. I guess that kind of makes sense. So whatever the previous one was, so 2, 5, and 11. So kind of what I was saying there. So if we tried adding, we probably wouldn't have gotten what we were supposed to do. So double it and add 1. And then they continue on, same thing. So 23, if we double that, that would be 46. But then you have to add 1, so that'd be 47. 47, if we double that, it would be 94. And then add 1, we get 95. So yeah, that seems like the pattern that's going on. That seems like that is what's actually going on. So that's why they wrote it here, not me. And moving down to the next one. So let's go ahead and go to number 3. Again, hopefully you're writing these down. And if you don't have your packet, again, try to get your packet as soon as you can, or find a way to write down what's going on. If you miss anything and we don't have time to go back, don't forget there's always the videos. So you can check out the YouTube channel, which is where this is going to be posted. And then you can get them later. Okay, so if you're not going to get your packet for a day or 2, you can just hold on to your packet or until you get it, and then go to the YouTube video and then finish it out. All right, so 1, 4, 9, 16. 1, 4, 9, 16. Those numbers look familiar. Those would be perfect square numbers. And don't forget, a perfect square number is a number that you would multiply by itself. And that's what you get, is the perfect square. So like 1 is 1 times 1. 4 is 2 times 2. 9 is 3 times 3. 16 is 4 times 4. So if we continue that pattern, 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49, 8 times 8 is 64, 9 times 9 is 81. So they are all perfect squares. Each term is a perfect square. And this part seems like it would be a tough one to kind of get. But to find the nth term, you would just square n. So if I wanted the 10th term, I would just square 10. That would be 100. So that, if we had to continue on, the next one would be 100. Oh, yeah. All right, that one was actually kind of an easy one. All right, A, D, G, J, and all right, we got letters, and I don't have an alphabet. I don't have the alphabet posted anywhere, but it looks like they already have it here. So to generate the next term, skip 2 letters after the previous term. So so go down 2 letters. So A, B, C. So skip 2, and then that third one would be the one we're looking for. So that'd be D. And then skip 2, E, F, and then G would be the third one. Ooh. H, I, J would be the third one. So it looks like they're just sort of going by every third letter. So I guess you could also say it's every third letter. So add, count 3 letters for each one. All right, I guess that one wouldn't have been too difficult. And there's a couple of different ways you could say that. But I think they're trying to have you say the previous term, because if you look at all of these, it says previous term. Well, except for number 4, that one did not have previous term. But it looks like all of these have you doing something with one of the letters that one of the terms that were already there. So yeah, I guess if you can, when writing these out, kind of say previous term, whenever you can, because you're kind of using that as a starting point for the next ones and the ones down after that. All right, so let's go to number 5. So 7:30, 7:55, 8:20. And again, you can see what we're doing here. I'm just trying to make it go kind of quickly so that way you can copy this down. If you're a bit ahead. But it looks like what they're doing is they're just adding 25 minutes to the previous term, right? And these are all times, so each time they're just adding 25 minutes. So that one was pretty easy, actually, I think. Number 6, okay, I'm looking at that one. 31415. What would be the next parts? Well, in this case, I am kind of lucky because I do have a chart of pi. And it says right there, conjecture for each term is a digit of pi. To find that nth term, you would need to find the nth digit of pi. Well, I should say the nth digit in the decimal of pi. I know what they're saying and all, but well, with any of these, just write them however works out best. And then to fill it out, I think you would need that pie chart, and that would basically have the next numbers 9, 2, 6, 5, 3, and so on. That one was actually a pretty tough one. I don't think anybody would really be able to just look at that and say, okay, we're looking at pi. If you gave that to me right away, I'd be like, okay, what are we doing? Let's see, -2, add 3, -3. Add 4, doesn't make a whole lot of sense. Well, maybe the 314 would have been the doing the 314 would have been the thing that says, okay, well, that's what we're gonna do. All right, I'm gonna come down a little bit here in case you're still writing any of that stuff down. I'm gonna go ahead and leave it here for a second. In case anybody's still doing this part here, I'll leave it up, and then we'll move on to this part here. But I'll give you like a minute break or something. I'm gonna be right back. All right. All right, so that should be hopefully enough. I'm gonna move on down, and these last ones are gonna be gone for now. All right, let's see, a counter example, an example that shows a conjecture is false. So if somebody says something, and internet's full of these things. If you ever go into the internet, you know, you look at blogs and places where people post things, you'll always have somebody saying, well, you know, things are always this way or that way, or politicians are always this way. And then someone's always like, how do you, you know, what about this case here? You know, and they'll kind of give it an example or a story to prove them false. So that's kind of that would be a conjecture, you know, like when people are saying, well, here's a conspiracy theory or something like that. So I saw one, I actually see a bunch of these, but the one I'm thinking of is oh, the government is just trying to use social media so they have your picture. And then one guy in the comments is like, well, do you have a driver's license or an ID card? Well, it's kind of true, you know. I mean, why would they need to do that if they already have your picture at the, I mean, the government agencies can literally just type in your name and they got your driver's license picture right there. So they don't need your bathroom selfies or anything like that. Anyway, I know there's like 100 of them. I could probably think of a better example, but I guess that one's kind of, it works. So determine whether the conjecture is true or false. If it's false, provide a counter example. So if it's false, you know, what evidence do you have that it's false? That's the counter example. So the sum of any two consecutive integers is always odd. So like numbers on a number line, 1, 2, 3, 4, 5, 6, 7, and so on. If you add them, they're always going to be odd. Add 6 plus 7, you get 13. That's odd. 7 and 8, that's 15. That's odd. 9 and 10 would be 19, and so on. So yeah, it does seem like that because, you know, every number on the number line goes odd, even, odd, even, odd, even, odd, even. And if you add an odd number to an even number, it's always going to be an odd number. The only way you can get even numbers is to add two even numbers or add two odd numbers. But since we're talking consecutive numbers, that's not going to happen. You know, numbers are not going to be skipping any numbers. So you're always going to have an odd, even, odd, even. All right, so that one was true, so we don't need to do anything. If it's true, it's true. All right, number 8, the product of two numbers is always larger than either number. So product means you're multiplying it. So you're multiplying two numbers, and it would have to be larger. And that kind of makes sense at first, right? So if I have 2 times 2, that'd be 4, and 4 is bigger than those two numbers. If I put like 8 times 9, right? 8 times 9 would be 72. So 72 is bigger than 8 times 9. But then people also forget that you can have fractions as well. So if you have a fraction, well, okay, you know, you guys are not my same students from Algebra 2, but this is one of those ones that I kind of point out every time it pops up. And that is if you multiply by a fraction where the bottom number is bigger, you're actually going to get a smaller number. So if you were in my algebra class, you would probably know this one right out, like immediately. So some students might even mark this as true because, again, they forget fractions exist. So if I have half of 2, which is one way I could read this, or 2 times 1/2, right? If you divide something in half, you're just basically dividing it by 2, and that's 1. Or I could also use my zero product property and say 0 times 5 would be 0. Anything times 0 is always going to be 0, right? So and 0 is always going to be smaller than any number you're multiplying it by. So either of these two examples will prove that this is not always true. Product of two numbers is not always larger than either of those numbers. So again, if it's false, you have to kind of show an example of how it's false. All right, next, number 9, the product of two perfect squares is always a perfect square. I guess we could try that out. So we could try like, let's see, perfect square number. So we could go with 16 times 25. I don't know, 16 times 25, just to try it out. And we get 400, which actually 400 is the square of 20 times 20. So if we take 20 and square it, that gives us 400. You know, I actually did. I don't think I know that one. I think I might have known, but this is the first time I'm actually like having it proven to me. So that kind of makes sense. And we could try a couple of other numbers, but you can see right there that it's true that if we take any perfect square numbers and multiply them, we are going to get another perfect square. Neat. Did not, again, I feel like I kind of knew that, but I guess it's been proven now. So anyway, let's see what we got here. The area of a rectangle is 6 meters squared. The dimensions must be 2 meters by 3 meters. Okay, well, if something is 6 meters squared, in this case it says false, we could also pick one that is 1 meter wide and 6 meters long. So it doesn't have to be. You could probably also find another combination too, like maybe something with decimals or something that would also work out. But there's a lot of other things you could try out. There's a lot of ways to get a rectangle that is 6 meters squared. I don't know if you could get a now you couldn't get a you couldn't really get a square out of that. You couldn't get a, well, you probably could get a square, but it wouldn't be a nice meter of this and that. Okay. Let's see what's over here. So I'm going to move down again. 11. So dividing by 2 is always a result less than the original number. Kind of similar to that one that we have with multiplying, right? So if we divide something by 2, it's always going to be a smaller number. And that's false because, again, fractions are one of those things that will usually kind of mess things up, right? Fractions are fractions are kind of that weird bunch that sort of just, well, I'm not going to say they play by their own rules or they have their own rules, but yeah, they do kind of act a little weird. I don't have one ready to go, but I don't know. I saw this one this weekend and it kind of made me crack up a little bit. And it's that Omni-Man meme. And it's the one where he's always like, look what they have to do to match a fraction of our power. But then in this case, it just he just says, look, a fraction. And it's just a half flying around back there. All right, man. I don't know. But yeah, fractions will throw it away. So if I divide by 2, so if I have -8, right, and a negative number, actually in this case, it looks like they're using a negative number. -8 divided by 2 is -4, which if you remember with negatives, negatives, when you have 2 negative options and you want to know which one's bigger, you want to go with the one that's closer to 0 or is less, because in negatives, that's like, sometimes it's like something you don't want to have. So if it's something you don't want to have less of it if you can't have 0 of it. Or like in this case here, we can get 0. So 0 divided by 2 is 0. So 0, and there is 0 is another one of those things that kind of plays by its own rules, right? Because 0 just sort of does its own thing. So if you take 0 and divide it by 2, well, it's not going to be smaller or bigger, for that matter, than what we already had. So 0 just stays 0. Okay, hold on. I'm trying to find my eraser. All right, that was not good. All right, next one here, 12. Vertical angles are never complementary angles. So vertical angles, if you remember, that's the one that, vertical angles, like if you were to just draw a line and then another line, vertical angles are the ones that are basically opposite of each other. Vertical angles are never complementary. So complementary meant that 90 degrees, right? So that means it's 90 degrees. Well, there's a lot of them, and you probably have to do a lot of playing with what's going on. But if you pick ones that are 45 degrees, so this may or may not be exactly 45 degrees, but if I could take this angle here and stack it on that angle, I would have a 90-degree angle. So yeah, if the vertical angles were 45 degrees, then they could be complementary. But that one, again, would require either a really good understanding or a lot of trying stuff out to make sure it works out. So yeah, anyway, number 13, if A times B is equal to 0, then either A has to be 0 or B has to be equal to 0. Okay, that's true. And that is actually what we would call the zero product property. And it says that if you get 0 as the product, meaning, again, product means what you get from multiplying, then one of them has to be 0. And that's actually a number property. So yeah, it would be pretty easy if you knew that, or you could, again, try playing with other numbers. 0 times anything is always going to be 0. So you could try all sorts of things. All right, so number 14, two angles supplementary to the same angle must be congruent. Two angles supplementary to the same angle, So that means it adds up to 180 degrees. The same angle must be congruent. Two supplementary angles. Oh no, two angles supplementary to the same angle. I think they're talking about two 90-degree angles is what my guess is. But that's good though, it just says true, so I'm not 100% sure on what's exactly going on with that one. I guess I could sit here and try to figure it out a little bit more, but it looks like we're, anyway, next one here, number 15. So this one's not really a math one, but maybe somebody might say, well, all states have at least 2 syllables, right? And a lot of states are pretty long. Some are pretty short, like Arizona. Arizona. So is that 4? Arizona. Or is it 3? Well, anyway, it's more than 2. And we could try Ohio, Kansas, Pennsylvania. Yeah, it would seem like that. And so you'd probably have to go get a list and see how many there are. But then here it says, well, no, that's false because Maine has 1 syllable. Maine is one of those states, I think it's oftentimes forgotten. I mean, people don't forget it, but like, if I told people to name 50 states, I don't know how many states they could actually name. Probably about half of them is what I would guess. But I'm sure if you were to look at most of them, most people would have forgotten Maine. I'm pretty sure everybody would remember New York, California, Florida, their own state, and Texas. For some reason, those are like the states nobody forgets. Anyway, next one. Squaring a number and adding 1 will result in an even number. So this is false because, well, 10 squared, if you add 1, that'd be 101. Or 4 squared plus 1, it would be 17. So those are 2 examples that work out. And for 17 and 18, you're going to have to write your own. And again, it doesn't have to be math. But you could say something, and it has to be able to be proven false, though. So that other example with the conspiracy theory, no, that's not going to work out because, well, I guess it could work out, but let's try to keep things a little bit more simple. Like, I don't know, okay, now that I said it, you can't use it. But like, all bugs are ants. Okay, so in that case, it would be false. And, well, I could think of any bug that is not an ant. You know, I could think of a fly, or I don't know if a caterpillar would really count as a bug. It's weird when you say bugs, like people, you know, like if someone sees a spider and they're like, oh no, a bug. It's like, no, spiders aren't bugs, they're arachnids. And it's like, okay, well, does it have to be an insect in order to be a bug? And then like people will say like, oh, bugs are, I was told this one too. I don't know if this is true, but they say bugs are like pests or blood drinkers or something. Like they bite, like a bed bug or a mosquito would be considered bugs. So like it actually has to bite you in order to be considered a bug. I don't know if that's true, because like everybody I know uses bug to mean like any insect or creature they don't want there. Anything that's not a mammal, pretty much, or a bird. So I don't know if that's true. It could be something like all cars are small. You know, something like that. But you know, I could think of a large car. If you could think of a really large car, you know, that would work out. Kind of brings me to another argument, but something like that. You know, something that can be proven true or false. I'm gonna try to pick something that's true though. Something that is always, pretty much almost always true. It doesn't have to be like 100% true, but 99% true, which I know is like one thing that usually happens with on the internet, is that sometimes in those blogs and places that I was just talking about, sometimes their reasoning is actually very sound, and the one in counter example that they can pick out is like the 1 in a million that could happen. Trying to think of something that would always be true. Something that is always true. I'd have to bring my phone out for this one. I don't have a lot of these ready to go, so I'd have to actually look. But then I don't know, that'd take a long time as well. But it can't be opinion either. So one thing that might happen is like, who's that one guy that made the movie Inception? He made a lot of movies. Christopher Nolan. He made the Batman movies, the Inception movies, a movie about like magicians. He made like, I don't know, a dozen movies or so, probably more. But it's like, you can't say something like, oh, well, Christopher Nolan doesn't make a bad movie, because what you think is a bad movie is probably different than what somebody else would consider to be a bad movie. Like in my case, I don't really like the third Batman. I mean, the first two were pretty good, and like the second one was like a hardcore classic. You know, it's one of those movies that everybody knows every scene by heart. And the first one wasn't bad. In fact, I actually like the second. I'm sorry, I actually like the first one a lot. Not as much as the second one, but it really does have its own. It really has its own everything. Yeah, I got like 20 more minutes. We'll probably go over some of these later. But I'm gonna move on to the next one just because it's like, again, we have like 20 whole minutes, and we'll probably get through to about there. And then we'll go ahead and break it off for independent study time. All right, anyway, if you ever have a chance to watch anything Christopher Nolan, it's pretty good. You know, a lot of them will get you thinking. And in a way, I kind of feel like Batman, the third one, was just like, what else are they gonna do? You know, and it's too bad the guy who plays the Joker wasn't around anymore. I would have been great to see him again. But then I guess it was kind of well, I mean, it makes the movie kind of more special, the second one, because, you know, the whole thing about that. Anyway, sorry. I'm just not a big fan of the third one. Let's see, a statement is a sentence that is either true or false. So we already got some true and false things. This is called the truth value, represented by letters such as P and Q. So example, supplementary angles have a sum of 180. Well, that truth value would be true because it is true. That is actually the definition of a supplementary angle, is that it combines up to 180. Negation, so like negate something or negative. So in other words, it's opposite of the truth. So the statement has the opposite truth value shown by the symbol, the squiggly line, and it means not. Okay, so it means not P. So here, they have that not P, so it means not true. Supplementary angles do not have a sum of 180. So they took the same thing and they said, well, okay, so it's not. So the truth value would be F. All right. Next one here, compound statements. So compound statements have to be joined by the words and or. So, and this is one that I think even nowadays I have people that kind of mess this up. And sometimes when I'm on the internet, people like, I'm like, do you mean and? You know, reading what they read is like, do you mean and or did you mean or? So statements joined by the word and would be written as P, and then this the thing that's pointing upwards. And you can kind of think of it like it looks like an A, right? So it looks like an A, but it's missing that little bridge between the points or the sides. So that's true when both statements are true. So again, and you need both of those things to be true. And the classic example I always give is, imagine that you're trying to apply for a job. Okay, so most jobs that require you to be outside the building require you to have a license, a driver's license. So maybe as you're applying for a job, the job listing will say, must have a driver's license and must be older than 18. All right, so you have to have both of those things. So maybe we're applying for like a truck driver, or one time a while back, I was gonna apply for driving a Pepsi truck. And that's what they said. They said you need a license and be older than 18. So in that case, you know, this is only a few years ago. So I was like, you know, I could do that. I have a license and I'm older than 18. So yes, I have fulfilled both of those. Now, if anyone in this room tried to do that, they would probably be denied because, well, most students in my classes are not older than 18. Okay, sometimes I will get a few, but maybe I'll have like one or two of them that would be able to join, but majority of them would not be able to get that job because they're not older than 18. Or if I said older than 21. All right, so older than 21, yeah, absolutely nobody would be, because if you're over 21, you shouldn't be in any of these classes. That's when you age out. All right, so next one here. So that's the and word. So again, both of them have to be true. And here we have a disjunction, so it can be joined by the word or. So we write it as P, and then we have this V. Now this one doesn't make as much sense because that V sign is something we don't normally see all that much. But just remember that one of them is or, one of them is and the and one kind of looks like it starts with an A, whereas this one starts with something that looks like a V. So P or Q, so either one of those is true. So if one of them is true, that makes me happy. So think of it this way, like what if I said, well, someone asks me, what do you want to eat today? You know, maybe we're driving around Flag and I say, I want pasta or quesadilla. You know, so I'll usually give two options, or maybe even more than that. You know, just as an example, I said, I want either pizza or quesadilla. And whoever else is there with me might think, okay, well, those are some good options. Let's go with pizza or something like that. You know, in that case, I'm happy. I'm happy that they picked one of my options because, you know, I could have done either one. Or if they had picked quesadilla, I would still be happy because that was one of the options that I gave. But if I gave out, that same option, pizza or quesadilla, I'll be happy. And then they said, okay, well, let's go get Chinese food. Then I'll be like, well, actually, no, I'd be okay with that. I'm okay with Chinese food. Or what if they gave you something that I don't like? Well, that's kind of hard. I don't know very many foods that I don't like enough to where I wouldn't want to go there if I was taken there. Well, there is one kind of food, and that's usually food that has a lot of eggs in it. I mean, for me, eggs are breakfast food. So if it's lunchtime and someone takes me to like Mike and Rhonda's, yeah, I'm probably gonna order like something else. Anyway, but that's the or statement. Either option will make us happy. And it's true when at least one statement is true. So like back to the job thingy, a lot of jobs will require some kind of identification. Usually they'll say something like, you will need an ID card or a driver's license, which they kind of do function as the same thing, except an ID card doesn't allow you to drive a vehicle, well, legally. But if you had either of those things, officer might say, well, can I see an ID? And you give them a driver's license, they'll be fine with that. They're not gonna be mad about that. And sometimes they'll accept other IDs as well. They'll accept like a military ID, they'll accept a work ID, something that looks legit. Probably not like, I don't know, something without a picture on it. So like maybe a social security card would be something they wouldn't accept because, yeah, you have the card, but that doesn't prove who you are. I mean, if someone said, oh yeah, here's my ID, and it was obviously like somebody else, like like if I showed an ID card and it was obviously like, I don't know, a guy from Europe or something, or obviously like an Asian person or something, that would obviously not be me. Something like that. Something that's like so very different. Anyway, so that's and an or statement. So I see a lot of people confuse those two. So don't confuse them. All right, write compound statements using the statements below and determine the truth value. So they give us 3 of them. So P, Q, and R. P says that there are 7 days in a week. March has exactly 30 days. Halloween is on October 31st. So P and Q. So that's the and symbol. Remember, it kind of looks like a A. So that's how you remember it. So in this case here, it says there are 7 days in a week. And there's that thing. Q says March has exactly 30 days. So that's all we did was just write it down. There are 7 days in a week and March has exactly 30 days. Well, if we have a calendar, which I don't have a calendar in here. I do, but it's not the regular kind of calendar. But if I remember, March has 31 days. Actually, I can check it on my computer. I mean, it says it right there too, but I'm kind of like, is that true? Yeah, as far as I know, every March has 31 days. And that's false, because March does not have exactly 30 days. All right, March, and let's go to the next one. So Q and R. So March has exactly 30 days, and Halloween is on October 31st. So we're given 2 options, and remember, and means both of them need to be true. So March has 30 days, that's already false. Halloween is on October 31st, that's true. But in an and statement, both of them need to be true. So well, this whole thing is all false. Because if one of them is false, then it's all false. All right, next one. So there are 7 days in a week, and October 31st is Halloween. And let's see, again, with the and statement, they need to both be true. So there are 7 days in a week, that's true. There's always 7 days in a week. And Halloween is on October 31st, that's always true. So since both of them are true, then the truth value is true. All right, and it looks like you'd have to use the chart on the last one. So I'm going to kind of go through these a little bit quicker. And I think, like I said, we're probably going to be done here for now. And yeah, there's no sense in me kind of pulling the lesson longer than it needs to be. So when we're done with this page, we'll be done. We'll probably go to the next one after we come back. All right, so this one's, remember that sign here means not P. So there are not 7 days in a week. Because remember, that's what it says. P says there are 7 days in a week. So it says not 7 days in a week. And that's the and symbol. And March has exactly 30 days. So in this case here, we already know that the 30 days one is false. And it says there are not 7 days. Well, that's false. There's always got to be 7 days. I've never heard of a 6-day week. Well, a counterexample to that, dang, I'd have to go on a whole different thing about it. But there was a time in, I don't remember exactly what time, I think it was like in the year 1750, and I'm not 100% on the date about that, but they actually did skip a few weeks in what they did. I think they still kept the weeks, but they switched the days, and this has to go with leap years. So like when they first discovered, you know, the Earth goes around the sun every 365 days, which almost everybody knew that. Everybody on Earth knew that. And anybody who tracks the sun would know that there would be about 365 days. But what they did not account for was that leap year day, that quarter of a day that builds every year. So for 1,700 years or so, we did not count the leap days, and that caused there to be like 100 extra days in the year. So at some point they were like, hey, wait a minute, those seasons no longer match what we're doing. So they just skipped a couple of months, and to account for all that time. It's one of those things that very few people know about, but I think, and there's only like one YouTube video I've ever seen about it. But yeah, they skipped a whole bunch of days at some point so they could get back on the calendar year. Anyway, sorry about that. All right, P or V. There are 7 days in a week, or Halloween is on October 31st. So in this case, with the or statement, if even one of them is true, then that means both of them, or sorry, the whole statement is true. In this case, yes, it's true. There are 7 days in a week, and Halloween is on October 31st. So that would be true overall. All right, so not Q, so this one is the March one. So March does not have exactly 30 days. So that's actually true. Remember, March doesn't have 30 days. It has 31 days. But it says it does not have 30 days, but that's true. It doesn't have 30 days. And it also says Halloween is on October 31st. That is also true. So that one, again, if it says it's not true, you know, it's like if I said something like, if I said my shirt is not red, that's actually true because it isn't red. So when you see the not statements, you got to also think about those as well. You know, you got to think, it's not that. Anyway, let's move on to number 7. So there are not 7 days in a week, or Halloween is not on October 31st. Well, here it says there's not 7 days in a week. And again, it always has to have 7-day weeks. Halloween is not on October 31st. Well, they have the little squiggly line R, which means not. In this case, that's not true. And Halloween is not on October 31st. That's false. So both of them are false. That would make this one false. And let's see, not P and not G. So there are not 7 days in a week, which is false. Or March does not exactly have 30 days. Now, again, when you have an or statement, if one of them is true, that means the whole statement could be true. March does not have exactly 30 days. That's true, which makes the whole overall truth value true. All right. So again, or means that either option of the given options are good. Yeah, I'll be happy with those ones. So I think we're done for now. I'm going to go ahead and pause the video.